Suppose a, b, and c are sets, and f is a function from a to b. Okay, so a, b, and c, right there, and c. Okay, and f is a function from a to b. Okay, prove that if f is onto, okay, and g and h are both functions from b to c. So we've got two functions going on here, g and h. And moreover, if the composition of g with f is equal to the composition of h with f, then g and h actually have to be equal. Okay. Now that last statement there, you might think to yourself, that's probably always true, because we're really just sort of canceling the f from the right of each side to get g equals h, right? But it turns out this assumption that f is onto is actually required there. It's not necessarily true without that assumption. All right, so how are we going to prove that g equals h? Well, remember, functions are relations, and so at the end of the day, they're sets of ordered pairs, right? So you could think of this as equality of sets, and just show that for every ordered pair, it's in G if and only if it's in H. Okay, but that's a little bit of a pain notationally. And so remember, if we know we have two functions, then it's a lot easier just to show that for every element, in this case B in the domain B, so for every B in B, G of B is equal to H of B, right? Just show that the functions always give the same value, same output for any input, and then they must be the same function. So let's let B be an arbitrary element B. As you see, we're doing the proof over here, and we have to show that G of B is the same thing as H of B. Okay, and well, what are we going to use here? We know f is onto, which immediately tells us that B is in the range of f, right? There's some A back here in A which maps to B under f. And that's nice because, remember, we know something about the composition of these functions with f, okay? And, look, if AB is in f and B, G of B is in G, then A to G of B is in G composed with f, right? And if A to B is in f and B H of B is in H, then A H of B is in H composed with f. And come back, where'd you go? There it is. Okay, but we know these are the same function, right? So if we take a single input and you map it by this same function under two different names, you can only get one thing, right? For a function, the output is unique. And so that does imply that G of B equals H of B, which was our goal. That shows that for any input B, G and H give the same output. Okay, so go ahead and try and write out the proof from the picture, or just read through what I have here. If you'd like some more detail, here's the sort of nuts and bolts. Okay, and then we'll get back to part B after this. So there's all the givens. Right? I'm already doing direct proof to suppose these three things are true, leaving me with a goal of G equals H. And as we said, to prove that these two functions are equal, we're just going to show that for any B in the domain capital B, the outputs of those two functions are the same. Write out the definition of f being onto. Let B be arbitrary. And we can do universal instantiation then to get this statement, right? Which was just f being onto. Okay, write out the definition of these compositions being equal, which we do just like we did this one over here. I'm using A and A now because these are functions from A to C, right? So the domain is capital A. Existential instantiation gives us some A naught which maps to B. And then, okay, we do universal instantiation where A is A naught to get that sort of both of the compositions applied to A naught must be the same thing, since after all these are the same function. And just rewrite that in the other notation. Okay, and use the fact that f of a naught is exactly b to get that. Well, just replace f of a naught here on each side by b, and you get g of b equals h of b. Okay, so that takes care of part A. Now, part B says, suppose C has at least two elements, and for all functions g and h from b to c, if g composed with f equals h composed with f, then g equals h. All right, prove that f is onto. Okay, this is sort of a converse to part A, right? Part A, you know, is sort of suppose f is onto, right? And then, you know, on some level, we had that if we were showing that if the compositions are equal, then g equals h. Okay. Now we're supposing that we do have that conditional, right? That if the compositions are equal and g equals h, for every possible g and h, and then we're getting that f is onto out of that. Okay. And for some reason we have to have this additional assumption here that C has at least two elements. So it'd be worthwhile to think through why we need that. Okay, what happens if C just has one element? Well, the quick answer is if you have a function mapping into a set with one element, I mean, there's not many things that function could be. There's only one possible function. It has to map everything to that single element. So, so then these compositions aren't going to tell us much. Okay. All right. So let's draw a picture of this guy. This problem is actually quite tricky, but I like it a lot because it has a really different feel from a lot of what we've done. Okay. And so my sets are getting sloppier here. So it's a really good example to work through just to see something a little different. So I'm trying to prove that f is onto, right? And well, actually, I'm going to prove the contrapositive. Okay, you see that in my proof here. So suppose f is not onto, and then we must show the negation of this if-then statement, right? If the compositions are equal, then g equals h. And the negation of that conditional, well, that conditional is false if these are equal, but g is not equal to h. Okay, so we must show there exist functions g and h from b to c such that the compositions are equal, but the original functions were not. All right, well, how are we going to cook up this g and h? What do we have to work with? We know C has at least two elements, so let's go ahead and name them. Call them C1 and C2. Okay, when we know they're not equal, I could put a not equal sign here if I wanted to. There might be a bunch of other elements here too, but we at least have two of them to work with. And then we're also, remember, proving the contrapositive, so we're supposing f is not onto. That means that there's something here in B which is not in the range of f, right? Remember, we have f here and g and h here. So I have some B here which is not in the range of f. There's nothing in A which maps to it. Okay, so I've got these three elements to work with, and I need to somehow define functions g and h, which are different, but when I compose with f, they're the same. Okay, and the trick is to make g and h almost the same, but to make them differ only on what they do to b. Okay, but when you compose with f, since you can't get to b from f, you're never going to see that discrepancy after you compose with f. Okay, so after you compose with f, they'll be the same, even though the functions are slightly different. All right, so how do we define these things? Well, if you look here, I'm going to define g to be b times c1. Right? Remember, this is just a set of ordered pairs. It's a Cartesian product. Oh, that's a typo though. There should be some. I wonder if I can write on this without. Maybe not. It should be curly braces around that. It should be the set consisting just of c1. Okay, that's a typo. Although sometimes people write it that way when they're being lazy. Okay, so basically that's every ordered pair where the first coordinate is in B and the second one is C1. So I'm just, G is the function which maps the entire set to C1. Okay, and H is going to be almost the same thing. It's going to map everything except for B to C1, and it's going to map B itself to C2. Okay, so B itself is mapping to C2, and everything else, I'll draw a dotted line for everything else, is mapping to C1. Okay, so that's what H does. And what am I trying to conclude? Okay, well, G not equal to H. I actually did that down here a second. You believe me there, right? Because they take different values on B. Right? G maps B to C1, whereas H maps B to C2. So these functions are not equal. That's right here. We're also supposed to show that the compositions are equal, right? So, well, take any A here in A, and you can think about, what would G composed with F of A be? Well, you do the F, and you get something other than B, right? And then you apply G. Well, G of everything here is C1, and so G composed with F of A is going to be C1. And H, okay, H composed with F, so you do F, you get the same thing here. This is F of A, if I had space to write it. But then we know that F of A is not equal to B, since B is not in the range of F. And everything not equal to B, H sends also to C1, okay? So G composed with F of A is C1. H composed with F of A is also C1, so the two compositions are indeed equal. Okay, well, that one may be a little bit hard to fully grasp from the picture. Let's go ahead and work out the details. So here's our assumption. C has at least two elements, and for every G and H you can come up with, if the compositions are equal, the functions must be equal. Okay, and we're trying to prove F is onto, and we are going to prove the contrapositive. Now that's a little strange. I probably should have put this over here and said if this, then this, right? Have it all as a goal and then the contrapositive, but I suppose I probably didn't have space for that. So if I were going to do direct proof, this is what I would see, right? And I've kind of flipped it around to denote that I'm proving the contrapositive. All right, so if we negate all this, then the universal quantifiers change to existential quantifiers, and then we have to negate this conditional, which you take the first statement and then you negate the second statement. Okay, so you've got these two elements, so there they are. F's not onto, put a not symbol in front of the definition of F being onto. And if we go ahead and push that not symbol in, we change both of our quantifiers to the opposite of what they were, and this equals becomes not equals. Existential instantiation gives us the C1 and C2 and C, which are different from one another. And existential instantiation gives us a B naught and B. Okay, so there's the three elements we were working with, C1, C2, and B naught. And we're going to have to use those to cook up a G and an H. Okay, and so it's a little strange. I haven't said what G and H are. So once I say that, we're going to have to prove that G is a function from B to C, and so is H, and then that this conjunction is true. Okay, so there we go. So with a little bit of creativity, as I explained in the picture, we make G and H almost the same. I have the same typo here. This should be B times the set containing C1. So G maps everything in B to C1, and H maps everything in B except for B naught to C1, and it maps B naught to C2. Okay, so they're almost the same except for what they do to B naught. All right, well, there's certainly functions from B to C. And we've got these two goals, and for the first goal, the compositions are equal. We got to show that for every input, their outputs are the same. And to show that these are not the same function, well, if you write out the similar definition and then negate it, you got to find some input B and B such that the outputs are not the same. Okay. So for this one, we will let A be arbitrary, and okay, so that I'm just proving the first one right now. This A being arbitrary is not for the second one. Remember, you don't want to prove the two goals at the same time. All right, so universal instantiation on the A gives us that nothing maps to B naught, right? So in particular, this A does not map to B naught. And oh no, running out of space. Let me shrink this font just a little bit here. Maybe we can see more of it. Okay, so from that we get that, well, G maps everything to C1, right? That's the moral from the definition of G, whereas H maps everything other than B naught to C1, and f of A is not B naught, so f of A does get mapped by H to C1 as well. Okay, and well, just looking at the so G of f of A and the H of f of A, they're both C1, so those are equal as desired. And looking at the B naught itself, we see that G maps B naught to C1 and H maps it to C2. And so B naught is an example of something in B for which G and H have different values. Okay. And that finishes the proof. So go ahead and read through it over here. See that what we wrote up is hopefully a good description of what we did over here. And we're done.